Hello everyone, my name is Yefeng. I am a PhD student in Tsinghua University. Today I will share my research on multigrid Dendrite growth model and its application in additive manufacturing. Additive manufacturing has been widely applied in aerospace and aviation and medical industry. The material usually used is titanium alloy, aluminum alloy, and nickel-based superalloy. However, there are still some barriers for the wide application of additive manufacturing. For example, the undesirable microstructure, and the second one is the defects, such as porosity and cracking as shown in these two figures. This formation of undesirable microstructure and defects are all related to the Dendrite growth process. However, using the conventional experimentation method, we cannot observe the Dendrite growth process directly. Numerical modeling could produce the Dendrite growth process, thereby help us investigate the Dendrite growth process in AM. First, we need to have a Dendrite growth models. There are two critical issues need to solve in Dendrite growth model. The first one is to achieve the simulation of dendrites with arbitrary orientations, and the second one is to be quantitative accurate. There are two types of Dendrite growth model. The first one use the virtual front tracking method. In this model, we need to create a virtual solid liquid interface, just like this figure shows. There are three different solid liquid interfaces. For example, some researchers use the descent square or octangent growth algorithm in 2D and 3D Dendrite growth model to consist the interface of the solid and liquid. Using this method, they can achieve the simulation of dendrites with arbitrary orientation very easily. However, since the established virtual solidly integrated interface is too complex, so it's usually hard to accurately evaluate the solid friction in the interfacial region. So it is hard to make this model quantitative accurate. Another type of Dendrite growth model use cell mass balance method. In this method, we do not need to build a virtual solid liquid interface. We just evaluate the interface movement by the evolution of solid friction, just like the figure shows here. Using this method, it is very easy to achieve quantitative accuracy because every movement of the interface is determined by the absolute equilibrium condition in the interfacial region. However, due to the nature of the anisotropy of the qubit cells, it is hard to achieve the arbitrary orientations. Some researchers adopt a orientation weight curvature calculation algorithm to achieve the arbitrary orientation. This means in their algorithm they need a very sophisticated curvature calculation algorithm, which is usually sensitivity to the cell size and the solidification condition. In our work, we developed a multi-grid 3D Dendrite growth model. This is based on the cellular automaton method. Just like a conventional cellular automaton model, we first divided our calculation domain into qubit cells. This is the big cells in this picture. And then we track the interface region and divide the qubit cells in the interface region into small qubit cells. We call it child grid. In the parent grid, we calculate the interface movement according to the solid absolute equilibrium condition in the interfacial region, and also calculate the diffusion in the Hoover calculation domain. And in the child grid, we use descent octangent growth algorithm. as shown in this picture, the octagon envelopes is located at the interfacial regions and consists of the virtual solid liquid interface. The movement of the interface is represented by the growth and capture of the octagon envelopes, and the growth of these envelopes is calculated by the movement of calculated in the parent grid. By running this algorithm, we can simulate the dendrite growth process step by step. This model have two advantages. First is we use decentered octagon growth algorithm, which make achieving the arbitrary orientations very easy. And second, the child grid help achieving the quantitative accuracy. We comprehensively verified our model. First is for the low-speed certification process. We first verified the model's ability in simulating the growth of dendrites with arbitrary orientations. Here shows the simulation result. We can see the model work very well. And secondly, we can verify our model quantitatively. We verify our model's ability by compare with the KGT model. We measured the tip radius and the tip velocity when the growth of the dendrites reach a steady state, and the red dot shows our simulation results of the tip velocity and tip radius at different undercooling, and the solid line is the prediction of KGT model. There are several lines. Each line is related to the prediction of KGT model use different surface energy isotropic coefficient. Comparing our simulation result with the different KGT prediction, we can determine the isotropic coefficient of our model, which is about 0.03. And then we extract the dendrite tip morphology and compare it with the Ivanov solution result and the shape of Fourier decomposition result, and we found a good consistency. We extract the certification condition from X-ray imaging observation result and use this data to simulate a dendrite growth process. We compare the simulation result morphologically and quantitatively, and we found a good consistency. This shows our model can be used for the dendrite growth in low-speed certification process. We then verify our model's ability in additive manufacturing condition. We carry out an experiment to verify our model. In this experiment, we run a EBM single track scanning, use the material of Inco 718. The preheating temperature is 856 degrees. The power is 400 watts. The scan speed is 0.5 meters per second. The beam diameter is 650 microns. Here shows the cross-section of the scanning of the track. And here is a thermal fluid simulation. We compare the melting pool boundary shape of the simulation result and the experimental result. We find the result are similar. We then extract the solidification condition in these three regions, region 1, region 2, and region 3, which is at different heights from the bottom of the melting pool. We get the temperature gradient and the cooling rate and calculate the solidification velocity, and then get the solidification velocity related partition coefficient and solute liquid slope, which then we used to in our dendrite growth model In here, we use the solidification velocity dependent partition coefficient and liquid slope so that we can take the solute trapping into consideration. We compared the simulation results and the experimental results. We focus on the two critical issues. The first one is the primary dendrite ion space, which indicates the size of the dendrites. We measured the primary dendrite ion space from the experimental results and also from the simulation result and plot the data result in this figure. We found a good consistency in the primary dendrite ion space. Another issue is the MB distribution. We carry out a light scanning of the MB distribution using EDS in a SEM machine. And here is the MB intensity tested by the EDS. And here is the simulation result extract from our simulation results. And we found the shape of the MB concentration is similar with the MB intensity curve. And the ratio between the highest MB concentration and the lowest MB concentration is similar to the highest MB intensity with the lowest MB intensity. This comparison shows our model can be used in additive manufacturing condition. Then we use this model to investigate the formation of sharing cage pores in additive manufacturing. Here, the sharing cage pores is the pores formed because the material sharing cage during the solidification cannot be fed by the liquid. The formation of these pores is very common in additive manufacturing. Here shows two experimental results. In these experimental results, we found a lot of sharing cage pores, such as this black dot in the experimental result, and the big pores in the green boundary. And these pores would be potential nucleation sites for cracking, and it would reduce the fatigue life of the components built by the additive manufacturing. We think there are two types of sharing cage pores, and they are of different shapes and should be caused by different mechanisms. These two types are shown in these two figures. The first one is the sharing cage pores between two dendrites. These dendrites have no misorientation. However, the second one is sharing cage pores at the green boundaries. The green boundary is usually the interdendritic regions of dendrites with different orientation. This means we have misorientation between dendrites. To investigate the formation of these two types of sharing cage pores, we run several simulations using the temperature gradient of 10 power 5 Kelvin per meter and cooling rate of 10 power 4 Kelvin per second. The temperature gradient and cooling rate comes from thermal fluid simulation results. To investigate the two types of sharing cage pores, we have different misorientation, 0, 10, and 20 degree. Here is the simulated dendrite structure. And at the simulation results with misorientations, the middle region is the green boundary region. We track the formation and the evolution of isolated liquid region. The first line is the isolated region we generated when the overall solid friction reached 90%. And this the second line is the isolated region when the calculation domain completely solidified. We first investigate the pores formed between dendrites without misorientation. We can see the simulation result. First, we can have a lot of pipe-shaped isolated regions when the solidification is 90%. And during the final solidification process, the shape is maintained. This means the isolated regions are not be further separated into small isolated regions and then form sharing cage pores. So we think the sharing cage pores in the interdendritic regions without misorientation is following the mechanism shown in this figure. First, we have a pipe-shaped isolated regions, and it solidified from the bottom to the top. This is caused by the temperature gradient, and at the bottom of the isolated region, the material has sharing cage, but it can't be fed by the liquid feeding from the top because of the surface resistance. So at the bottom of the isolated region, there is a sharing cage pores formed. And during the solidification process, the pores are formed one by one. And then we have a group of pores which is well aligned parallel to the dendrite orientation. Due to this sharing pairs is usually surrounded by the liquid during its formation and growth, so its shape is usually spherical. As for the pores formed between dendrites with misorientations, this also means the pores formed at the grid boundary area. The simulation result shows when the solidification is 90%, we will have fishbone shape isolated region at the grid boundary region, and during the final solidification process, this fishbone region are separated into small isolated regions. And in these isolated regions, we will have sharing cage pores formed. And due to the sharing cage pores formed and growth is restricted by the isolated regions, which is usually of irregular shape. So this sharing cage pores is usually of irregular shape. And due to this isolated region are usually solidified last, so it has a higher solute concentration. So there will be places the solute-rich precipitate form. So this sharing cage pores usually appear with solute-rich precipitates, just like this experiment result shows. The white one is a precipitate, and the black one is the sharing cage capacity. We then investigate the impact of cooling rate on the formation of sharing cage pores. We run two other simulations with a lower cooling rate. One is 2000 Kelvin per second, one is 5000 Kelvin per second. And to investigate the impact of cooling rate on the formation of sharing cage pores due to different mechanisms. Misorientation of 0 degree is carried out for mechanism 1, and the misorientation being 20 degree are carried out for mechanism 2. And we found as we decrease the cooling rate, the size of the pipe-shaped region and also the isolated region caused by the mechanism 1 and mechanism 2 are all increased. And we then see the simulated primary dendrite ion space, which is also the size of the dendrites. We found the tendency of the isolated region's size is is consistent with the tendency of the primary dendrite ion space. So we can know if the primary dendrite ion space is smaller, then we can get a smaller isolated regions, and then we can get a smaller sharing cage pores. However, whether the sharing cage pores can be formed and can be observed, first we need to consider the size of the sharing cage pores, or we can see the isolated regions. If the size is too small, maybe we cannot see it. This why we will have this consideration. We need to look at the formation of the new phases in the solidification process of the nickel-based superalloy. For example, usually first during the solidification process, first we get the gamma phases, and then we will have the precipitation of signal phases and the gamma prime phase. For example, the gamma prime phase have a lower density than the gamma phase, so its formation will have expansion. And the signal phase have a higher density, so its formation will have a sharing cage phenomenon. So the sharing cage and expansion caused by the formation of these phases, it would have enlarged or eliminated the sharing cage pores. Since the gamma prime phase have a much higher friction, expansion would have eliminated the sharing cage pores with small size. So from this discussion, we can have two possible elimination methods for the sharing cage pores. First is increase the cooling rate, so we can have a smaller sharing cage pores, which can be easily eliminated by the expansion of gamma prime phase. And the second one is the material improvement. For example, we can reduce the material sharing cage ratio. Then is the summary. First, we develop a multigrid dendrite growth model and verify it comprehensively. And second, the model is used to simulate the dendrite growth in EBM process, thereby verify its applicability in additive manufacturing condition. And second, we use this model to investigate the formation mechanism of sharing cage pores in additive manufacturing, and investigate the impact of cooling rates and the formation of new phases on the sharing cage pores. Thank you. That's all. Thank you.